Hi, welcome back. In this lecture I want to introduce probably the most famous 1-qubit quantum gate, that is the Hadamard quantum gate. So what does it do? Well, the Hadamard operation, in short also HAD, creates an equal superposition when presented with either 0 or 1 state as an input. So we start as an input like a classical bit, that is so either state 0 or state 1. We apply the Hadamard, and the Hadamard put our classical bit in a superposition. So it's changed from classical bit to a qubit. In some sense, the Hadamard gate is another gateway for quantum superposition. In particular, most of the quantum algorithms, they start from classical bit, and then apply Hadamard to go to the superposition. So we move to the quantum state, a real quantum system. So differently from the quantum knot we saw before, it does not have any conventional equivalent when it comes to a classical case. The symbol for the Hadamard gate is H, that is enclosed by a square. The Hadamard gate can be expressed by a unitary transformation that is also expressed by this matrix form here. So it's basically 1 over square root, and then we have 1, 1, 1, minus 1. I'll just remind you how to read this. So in case we have the input state 0 and 1, and then here we have the output state 0 and 1. So in this case, if we have the state as an input, then if you apply the Hadamard gate, we're going to have 1 over square root multiplied by 1 over square root of 2. So this is going square root of 2 state 0, and then 1 over square root of 2 multiplied by state 1. So this is a plus 1 over square root of 2 state 1. So you see that the probability is going to be the same for measuring either state 0 or 1 after the observation. Also check here that there's a difference in sign between this, right? So if you have the input, it will be, and you apply the Hadamard gate, you will have 1 over square root multiplied by the state 0 minus 1 over square root multiplied by state 1. So there is this slightly symmetry that we also will see in the next slide. If we want to represent this in making an operation in your quantum simulator, if you develop one, what you need to do is express your matrix in this way. You see here the different elements of the simple matrix, and then you apply this tensor to your qubit. If we look at the transformation of the Hadamard gate using the circle notation, what the Hadamard gate does is basically produce a uniform superposition. So we start from either state 0 or state 1, and we apply the Hadamard gate, and after we apply this, we will have the equal probability of finding the system either in state 0 and state 1. So you see the area here are actually the same. When we start from 0 or state 1. The only difference is here on the face, and this is to the difference we saw on this sign here. There is also this asymmetry in the circle notation. When we start from state 1 and we apply the Hadamard gate, we will have a relative phase of 180. In the previous slide, we saw the Hadamard gate applied to classical bit, so either state 0 and 1. Obviously, what we can do is to apply the Hadamard gate also to a qubit that is already in a superposition of state. In this case, the results, if we have a qubit that is in a superposition of state with a complex coefficient alpha that is multiplying the state 0 and the complex beta multiplying the state 1. The final results is basically still a superposition of the two state, but is a weighted superposition. So the multiply the state 0 by a plus beta divided by square root of 2. Remember that the square root of 2, when we calculate the probability in quantum computing, we take the module and then we take the square, right? So this is basically dividing in two ways the probability. But in the case of the state 0, we have a plus. In the case of state 1, we have a minus. As I said, the Hadamard gate is a quantum gate. That also means that must be unitary. That is, by definition, reversible. One interesting part is that the Hadamard gate is its own inverse. So, for instance, if we apply, twice the Hadamard gate, we will get the initial condition. So, if you start from the state 0, and then we apply the Hadamard gate, we go in the superposition, a perfect superposition, and then we apply to this superposition again the Hadamard gate, we will go back to the state 0. So here's a few examples using the circle notation. This is the last slides, and talk to you soon, and let's check another quantum gate.